Next, we have Q&A session. For that, I would like to invite Engineer Ashish Sapkota to moderate the session.
We will just take around 2 to 3 questions, and then we can wrap up this session. There is one question regarding the damping. So how do we know the damping is 5% for all the RC structure and is suitable for all the structures we are designing for?
Yeah. So as I mentioned, we don't know. Honestly, we don't know. This is just a simplified value that has been determined from a lot of testing and research, and a typical value that is used, and it is expected. So what is expected is that when an earthquake starts, the structure may be undamaged, so damping may be large. It might attract a lot of force at that point with an uncracked cross section and low damping. But as soon as that happens, because of the detailing that we have provided in the structures, the cracking will happen, and that cracking in some locations, and also the cracking of non-structural component and so on, will reduce the stiffness and also increase damping. So we are expecting, the codes are expecting that while the initial damping and initial cracking may be different for different structures, after some level of damage and some level of earthquake, they may go to have roughly the 5% damping that we use for the design, or close to that one. And it may increase. If the earthquake is strong, the damping may continue to increase with the damage. And also the stiffness reduction, same way. In the beginning, it may be gross, and then maybe a little bit less, and then a little bit further less. That's the assumption of the codes to make it simple. Like I said, the damping is the nonlinear dynamic analysis will start with 2% and will compute the damping as it goes through the damage cycles.
Even in different guidelines, they give different kind of values. So it depends on the project, maybe the location and other thing.
For different height, the damping will be different. So at tall buildings, we use smaller damping, and for lower buildings, we use larger damping to start with.
So let me take one question regarding to the time period. So there is one question. So when the natural period of two modes are significantly different, for example, T1 is 5 seconds and the T2 is 3 seconds. So what could it mean to the structure?
Yeah, so this point I've raised earlier, also in the previous webinar. This means that the two-direction stiffness of the structure is significantly different. And this is not actually a good thing to have in structure if we can avoid it, because then the response of the structure in exactly orthogonal direction is very different. But for a diagonal loading, then the structure may have unsymmetrical response because the stiffness is so different in the two direction, and it is okay for each direction to be sort of excited in exactly the same direction. But as soon as we have a 30-degree, 40-degree excitation, then the building will respond not in the direction of the loading, but it will kind of sway in another angle, because the principal direction will not match. So that will increase the unsymmetrical forces in the structure. So it's preferable to have a similar, closer natural periods on the two direction if possible.
Okay, so there is one question regarding to the modeling. So did we model the RC stairs in that model that we are showing today?
Yeah, it's a very good question. The modeling of the stairs for a high-rise building has no impact, because the stiffness is so small compared to the shear walls and columns, which are very large, and the effect of these stairs is almost negligible. So typically for tall buildings, it will not matter whether we model or we don't model. However, for a low-rise building, 2, 3-story, 4-story building, the stairs and the ramps, especially the ramps in the car parking, they become like struts, and they alter the stiffness of the structure, and they will increase the eccentricities because they will act as struts, and they will get a lot of axial force. And if we don't model them and they are present, you might get in the real structure unsymmetrical response, more shear forces in some columns, and so on. So I think, generally speaking, for low-rise buildings, staircase is better to model them if we can, and it's not difficult. And you will find that with that and without that, your structures, more shapes will be different.
Okay, so for today, let's take one last question. And this is related to the fixity support. So how to resolve the problem of the higher corner stress in shear wall base with fixed or pinned condition? Is reducing stiffness with 0.35 IG is the only way when the tensile stress governs?
Okay. So first of all, we don't reduce the shear wall stiffness by 0.35. I think it's the direction is probably less than that. But the thing is that at the shear wall, if you're modeling it by shell elements, then we normally put pin supports at each shell element because shell elements are distributed around the core wall. So as a whole, the wall becomes fixed. So it is not necessary to fix each node. It's actually better to put the pins at each node of the shell element, which is used to model the core wall. Whether you use fixed or pin, it will not matter much, except for some local effects in the first 1 or 2 stories. But modeling the foundation will actually reduce the moment in the core wall. Because if you model the foundation and model the soil, then the rotation of the soil and the rotation of the foundation, especially for building which is not very tall, will reduce the bending moment that you might get otherwise in the core wall. So I think that is kind of an important point.
So I think we will just do this for today. And the other remaining question, we will just incorporate them, give the solution, and then share it with email.